In this lecture, I will come back to the Ros2 command line tools you can use with the Ros2 interfaces, and in fact you've already seen most of them during this course. This will be kind of a global reminder, quick recap, and also I will add a few more tips. So first of all, let's source our bash RC, so we have all the custom interfaces that we have built previously. We are sure they are in this session. So you have the Ros2 interface command line tool. If I press tab twice, you can see we have a few commands, and you already used a lot Ros2 interface show. When you already know the message name, you can my robot interface, for example, with SRV compute rectangle area. When you already know the name of the interface, well, you can find it like that. Ros2 interface show example interfaces, let's say message string. You can find the data you need to send from there. So here you see we have primitive data types float and string. Okay, what you can do also is to do Ros2 interface list, and that will list all available Ros2 interface you have on your environment. And as you can see, that is, well, quite a lot. So that is everything you installed or built by yourself. So you have first messages, and then you can see we have services here. So you can see, for example, let's go here, example interfaces, they are all here. We have here geometry messages. Okay, you saw a little bit of geometry messages, for example, the twist and vector3. We saw that on the GitHub package, but actually they are installed. You also have sensor messages. And if we go to here, my robot interfaces, hardware status is listed here, and you have the same for services. My robot interfaces is here, and you can see the other services that you have. Okay, and what you can do also is, because this is the complete list, Ros2 interface package that will show you every message or every interface with messages and services inside one package. So for example, sensor messages, which is the name of the package, and you have all the interfaces from that package that you can use, and this is exactly what we saw on GitHub. So that are the most useful commands with Ros2 interface. And now let's do a quick recap with what you can do with interfaces and topic first. Let's start Ros2 run my Python package. Let's start a publisher. So okay, we have the hardware publisher, hardware status publisher. So here you can find easily what you need to send on the topic actually directly from the node. If we do Ros2 node list, okay, let's go from the node to the interface. So you have the list of nodes, and you see you have the hardware status publisher. So Ros2 node info with hardware status publisher, and you will see that in the publishers you have hardware status topic, and you also get the name of the interface. So from the node name you can directly find the topic and the name of the interface. You can also find it by doing Ros2 topic list. You see hardware status, and then Ros2 topic info hardware status, and you find the name of the interface, and then Ros2 interface show with my robot interface message hardware status. And directly from the node name or the topic name, you can find what you need to send or receive. And if we start now a service server, Ros2 run my package, let's start the add to int server that we already have. Okay, so here we will do the same thing. Ros2 node list, we see that we have a new node, so Ros2 node info add to int. On the service servers, we have add to int, the name of the service and the interface. And you can also find it with Ros2 service list. You see that we have the add to ints. You do Ros2 service type. Okay, with Ros2 topic, it would be info. Here it's type, add to int, and you get the name of the interface. And then you simply need to do Ros2 interface show example interfaces, SRV, add to int, and you get the interface. So the Ros2 command line tools for interfaces are quite useful to actually find what you need to send or receive or request, and you can also see all the available options that you get. And again, make sure to make the difference between the topics and interfaces. The topic is the communication layer, and the interface is what you send. And the same for services. The service is the communication layer, and the interface is what you send as a request and what you get as a response. This is the solution of the previous activity where you have to monitor a battery state and power on and off a LED panel accordingly. So I will separate the solution into 3 different steps so that it's easier for you to follow, and if you are stuck at one point, you can watch one solution, one step, and then continue to work on your own. So first of all, in this lecture, I will create the LED panel node and publish the LED panel state along with a custom message type. In the second lecture, I will create the service server inside the LED panel, also with a custom service type. And in the third lecture, I will create the battery node to monitor the state, and this battery node will call the setLED service. So let's get started. First, for our LED panel node, we need to create a custom message because this panel node will publish the LED panel state on a topic, and we don't have an interface for that message. So let's go inside our robot interfaces in the MSG folder, and here we will create LED state array dot MSG. Okay, so we have multiple LEDs, so we need an array, or you can put lists if you want, and we will send the LED state. So that's why I named it LED state array.msg. Now we can edit this file right here, and what we'll put inside here, I will use int 64 with an array LED states. Okay, so we use the primitive data type int64, and actually this is an array of this type. You may have used a Boolean array, because here the LED state will be only powered on or powered off, so you may have used a Boolean state, which is also fine, but here we use integers, 0 for off and 1 for on. So that message is actually quite simple, it's just an array of integers, nothing really fancy. And we will go to our symmetrist.txt to build it. Okay, don't forget this step, and I will add it here. So there is no specific order, okay, but I will first write MSG and then SRV just so it's more readable, and you can put the message here, MSG. Okay, we save the file, and now we will be able to compile the package with colcon build, and let's choose my robot interfaces. Okay, and compilation is now finished. Here I can source the bash rc and find if our interface is here, Ros2 interface, show my robot interfaces, MSG, and we have the LED state array, which is available here. So now we will create a node in the Python package. Let's call it LED panel.py and chmod plus x to make it executable. We can go in our Python package and again use template LED panel. So that will be LED panel node here and here LED panel. So the code structure is now ready. What we can do first is from my robot interfaces.msg import what LED state array. So we can import the message directly here. And what we will do is simply create a publisher, okay, to publish on a new topic with this message. So let's create LED states publisher, which will be self-create publisher with the name, with the type, sorry, LED state array. Name will be LED states, okay, and queue size of 10. So we have a publisher. Now we need to publish the LED states. What we will do here is to create a function, publish LED state, and here we will create a LED state array that we need to fill. So we need to fill the LED state field. Okay, this is the name you need to use. So msg.ledState, and here we need to give an array. Okay, so what we can do, instead of creating an array here, we can actually store the LED states in an array in our class, LED states. So let's say we have 3 LED, okay, and all LEDs are powered off. So we have 0, 0, and 0. So here we can use self LED states. Okay, we put the array inside the message, and simply we can publish LED states publisher, publish the message. Okay, and now let's create a timer, self LED state timer, self create timer with the duration. So, well, I didn't specify any duration, any frequency for this topic. You can choose whatever you want. Here I will use a duration which is quite high, for example, here 4 seconds. So it will publish every 4 seconds. We add the callback, publish LED state. I will do some auto formatting here. And well, the node is now finished. Not that hard, okay, it's just the same thing we already did twice in this course. We can now go to the setup.py and add here an executable, LED panel. That will be the executable, my Python package dot LED panel file, and that will be the main function as always. So we go back to our workspace and we can colcon build, packages select. We can build the Python package, and I will also use the symlink install flag here. So in that terminal, let's source bash rc. Let's run Ros2 run my Python package LED panel. Actually, I can add a log here. Self get logger info LED panel node has been started. Okay, so let's relaunch the node. As we used symlink install, we don't need to compile it again because it's a symlink link. Okay, LED panel node has been started, and here let's see what we get on the topic Ros2 and topic list. So we have the LED states topic, Ros2 topic echo LED states, and we should receive 1 message every 3 seconds. So let's see if we receive, okay, we have 1, and if you wait 3 more seconds, you have another one with the 3 LED states. Okay, so for now they are all at 0 because we just put 0 here. Well, so that's it for the first step of the solution. This is the second step of the activity solution for the LED panel node and the battery state. So we already have a LED panel node, which is publishing the LED states with a custom message. Now what we will do in this step is to actually create a service server inside this node to be able to change one of the LED value here from the outside. So we need a custom service type. Let's go to our source directory in my robot interfaces, SRV folder this time, and let's create set led.srv. So we can edit the file here in srv, set led, and we will need to write first the request. So as we want to set an LED in an array, we will first give the LED number, which will be an int 64. Okay, this will be the index inside the array, so integer, and we need to give the state for the LED. So here, as I used already integers to keep the state, I will keep using integers. You can use boolean, so it would work. You write 3 dashes, okay, because that is the end of the request. And now the response, let's simply give back a success flag, bool success, and that's it. So the LED panel node will need to check if it can change the state of the given LED number. If yes, it will return true. If not, it will return false. Let's add that to our CMake list here, srv set led.srv. Okay, and we can compile here using code build. Okay, and let's see the interface in the terminal. Source dbash rc and Ros2 interface show my robot interfaces. So if I press tab twice, you can see we start to have a few interfaces, and we have the set LED right here with exactly the definition we provided before. So now back to the node, we will import from my robot interfaces srv import set LED. Okay, and we will create a service server right here. Okay, so let's do it here. Self set LED service, and we will use the create service with the type set LED, the name. So name is quite obvious here, set LED. As you can see, it's also a verb. Okay, and we need callback, so we will write the callback here. Callback set LED. We have a request and a response. Okay, so we can put callback here, self callback set LED with some auto formatting. Okay, and here, okay, first I will simply do that let number request LED number. So when we use LED number, we just have this variable, and we don't need to write that every time. Okay, and state will be request.state. Okay, so basically, in this case we have 3 LED. So in that array, this will be index 0, index 1, and index 2. But we will suppose that for this request, the first LED will be named LED1, and then LED2, 3, 4, etc. So we will first need to match the LED number with an index in the array, and also we need to check that it already exists, okay? Because if you ask to change the LED number 1, okay, it's here. If you need to change the LED number 4, here actually we don't have an LED number 4, so you need to return an error. So we will add a condition if the LED number is greater than the length of LED states. So in this case, if we ask 4, here this will return 3, so that will fail. Or if LED number is below, is less or equal 0, in that case, it means, of course, the index doesn't exist. So we will do response.success false and return response directly. So that is usually something you need to do when, well, in any kind of situation in programming where you have a server side, you need to check the request from the client. It's not only specific to Ros2 services, it's for everything you program. So now we are sure the LED number is a correct number. And let's also check if the state is not 0, or if the state is not, actually we can, if state not in 0 and 1, we can also do that. Response success false and return response. You can also put all the checks together if you want. So now all the parameters we get are correct, and we will change the state for the given LED. So self LED state. So the index will be LED number minus 1, because we start counting at 1 here, and state. So the state will only be 0 or 1. We can do response.success true and return the response. Okay, and that's it for the callback. So first we check the parameters we got from the request. We validate each parameter, and then we do the action. So the action is simply to change the value in an array, and then we fill the response. Finally, we return the response. And one thing we can do here also is right here to publish the LED states just after we have changed it. Because what will happen here? This timer, we call the LED states every 4 seconds. Okay, so if you call this, and the last time the timer published was like 1 second before, then the last data you got from the topic is wrong. Okay, so you need to wait until the timer will trigger this callback again to get the new states. Here, we simply say that anyway, when we change the state, we directly publish it again once. So if you listen to the topic LED states, you will always have a correct value. Right, so now let's test that with, let's build it. Well, actually, we don't need because we have the CMake installed, but let's start the server again. And actually, we need to source badges because we've added a new interface. So let's sample LED panel. We have here LED states topic. Let's wait a few seconds. Yes, so we have LED states every 3 seconds. Now in this terminal, I will call the service. So let's check first that we have a service, Ros2 service list. Set LED here. Great. So Ros2 service type set LED, and we have the type. So now let's call it Ros2 call, Ros2 service call set LED with correct type, and we need to give. So let's do that. We need to give LED number. Let's put 1, and states let's put 1. So we want to change the first LED. Okay, so here it's still publishing, as you can see. Let's do that. Okay, and as you can see, we have a new value now. And just after, so we have just called in fact the service just after the LED states was published. And as you can see, it was just published after with the updated value, and now it is published with the correct value every time. So we have the request here, and thus the response success true. Okay, let's test different things. So if I do that with 0, okay, we directly have the new value here, which puts back the LED to 0. Now let's say I use 2. Okay, success false because it is not correct. I should put 1 or 0. Now let's say I put the correct value here, but I use 5, which is not correct. I will get success false because the fifth LED doesn't exist. So in this case, the return is quite, the response is quite basic. If you want, you can add a message also to give more details about what happened. And here, if you want, you can increase the size of the LED states array, okay, and you can put as many LED as you want to make different tests. So that is the end of the step number 2 of the solution. This is the part 3 and final part of the solution. And in this part, we will focus on the battery node. So the LED panel node is now complete, okay? It is publishing the LED states on a topic, and we can actually send a request to change one LED thanks to a Ros2 service. Now we will create a battery node. So in the source folder, again, my Python package, here, battery, we make it executable, and let's edit the file. So we take template, my battery node, here, battery. Okay, and we have the code structure. What we will do here is first we will check the battery state, and then we will call the set LED service. So 2 different steps here. So to check the battery states, of course we don't have any battery here. If you had a battery, then you would have to interact with the hardware to see how you can actually check the percentage of the battery, for example, or to see if the battery is empty or full. Here we will fake it, and we will simply say that we have a battery self battery states, and found out it is full at the beginning, and we will use empty as a string to say it is empty. So only 2 states here. And now we know that the battery battery state is full at the beginning. After 4 seconds it will be empty, and then it will be charging, and after 6 seconds it will be full again, etc. And if you want to check battery states at a given frequency, here that's what we will do. One common good solution is to use a timer. So we will have battery timer, self pre-timer, and let's say we want to check the battery at 10 Hz, so 0.1 second, and I will create a function here, check battery state. Okay, that we put here. So that is also a structure you can use for checking stuff with hardware. For now, we've used timers with publishers, but in fact, you can use it for anything else. So every 0.1 second at 10 Hz, this function will be called. And here you can simply check the battery state and determine if it is full or empty. So to fake it, I will compare the time. Every time I will compare the time with the last time it was full, and then the time with the last time it was empty. So I will add a new attribute here. Last time battery state changed. And this will be, so it's quite descriptive, the last time the battery state has changed. And we need the current time, at least at the beginning. So how to get the time? You have the time functionality from the time module in Python, but you can also get the time with Ros2 with the RCLPy library with nodes. So that's what we will do here, okay? I will create a function to get the time, get current time in seconds. Okay, and you can get the time with self get clock and now, okay? So you have a get clock method in your node, directly from your node, okay? And that will return a clock, and with now you can get the current time. And this is an object you can do seconds, nanoseconds to get after the seconds and nanoseconds as a tuple. So we will get that, and then we need to compute the seconds, because here I want to have the time in seconds as a float number. So what I will do is return seconds plus the nanoseconds. So this is an integer, this is an integer, so I will divide the nanoseconds by 1 with 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So we can convert that number into a second with float. And that's what we will do here, self get current time seconds. Okay, so we are getting the time directly from Ros functionality. So when we check battery state, we will check the time now, get current time seconds. So we know that what is the time right now, and we know what was the last time the battery state changed. So if the battery state is currently full, we will check that the time now is at least 4 seconds after the last time the battery state changed. So minus self last time battery state change is greater than 4.0, okay, because we are comparing seconds in float. So if the battery state is full and if we have waited 4 seconds, it means the battery state is empty. Self battery state will be empty, so I just write like that as a string. And let's print self get logger. Let's print something, info battery is empty, charging battery, okay. And we need to say that the last time the battery state changed is now. Self last time battery state changed equals time now. Okay, so now the battery will be empty, so we will add an else here to check when the battery is empty. And we will do the same thing if time now minus the last time is greater than 6 seconds here. Okay, we will wait 6 seconds. The battery state will be full again. We can print it. Get logger info battery is now full again. And the last time is the time now. Okay, so all that logic is just to actually simulate a battery state that will change between full and empty. And what we could do here is simply to say, okay, battery is full, then we wait for 4 seconds, we wait by blocking the thread, then the battery is empty, then we wait by blocking the thread, etc. But it's maybe a better practice to not make the thread be stuck here. So by checking at 10 Hz and doing that, we don't pause anything in the program. And let's test that first. Okay, we will add it here. Battery, my Python package, battery main. Let's compile this new file. Okay, let's do that here. Ros2 run my Python package with battery and okay, we are waiting. Okay, battery is empty, so you can see the timestamp here at 7, and then 6 seconds later, 13, battery is full again, and then 4 seconds later, battery is empty, etc. Okay, we can also add here just a log to say that the battery has been started. Battery node maybe. Okay, so when we launch it, we have battery node has been started, and then you get a log every 4 and 6 seconds and the state is updated. So now what we need to do, we need to set an LED when the battery is empty and to unset it when it is full. So we will create a client for the service. First, we will import from my robot interfaces srv, import set LED. Okay, so that is the same interface as for the server. And to create a client here, because as you can see, we already have some stuff running, so we can just, if you go back to the add to ins client, no OOP, here, we can just do that like spin until future complete because our node is already spinning and we already have some stuff going on. So we will use that functionality here that we've created. So we have a function to call the server, okay, and we have a callback to handle the response from the server. And okay, I don't usually copy and paste stuff apart from the template, but this, as I told you, is kind of a template you can use for any of your clients. So let's copy that in our battery. And here, I will paste it. And now we will just modify the names, okay, to make it match. And you will see it will be quite simple. So here we don't call the add to int server, we call the set LED server. We don't have A and B, we have LED number and state. So we create a client. We change the type, set LED. The name is set LED also. You need to make it match with the server. We wait for the service to be up. This doesn't change. Then we will change the request. So that will be a set LED request. So inside we have the request LED number. We set it. Request state. We can set it with state. We call the service asynchronously with the request, and we add a DOM callback. Callback will be here. So callback call set LED. So we can change it here also with future LED number. Let's run in the parameters so it makes more sense. And here we will have LED number equals LED number. State equals state. So we pass the LED number here to the callback and the state to the callback also. And here we have our try-catch structure. We don't change that, okay? We have the response future result, which will get the response. And if we have an exception, then we print that. Don't change. We will only change the way we handle what's inside the response. So here, of course, we will not print that. We can just print response.success. Okay. Maybe let's share because this is Boolean. So we just print true. We just print true or false. And well, it seems that that's it. So once you have a good template that works every time, well, just you can replace any value in template and you get functionality quite fast. So to recap, we first create a client, we wait for the service, we then create a request with what we got as parameters here. We call the service and we get a future object. So what we do is we add a DOM callback for the future object. So this will return. The node will continue to spin. This check battery state will continue to run, of course. And once the server responds, this callback will be called and we can manage and handle what we got with the response. And now, of course, we need to call this function in the code to actually make it work. So here, when we detect that the battery is empty at this point, directly after that, we will call self call set LED server and we will give a LED number. So let's say we want to change the third LED. State would be 1, okay, and right here, call set LED server with 3 and 0. So here we will power on the LED and power off the LED. And you just need to call one function like that, okay? You have kind of your template to call the server, and now you just need to do that in your code. So let's run it again. Now we will start the LED panel. Let's see what we get with LED state. Okay, it is publishing states. And now we run the battery node again. So it has been started, and let's see what happened. And yes, when you copy and paste, of course you can make some mistakes. We also need that include here, because we are using partial here, so we need to include it in code. So let's start it again. Okay. Callback set LED, but next. Yes. Okay, it should work now. Okay, so the battery is empty. Charging battery. True is the response from the server, which means it was successful. And as you can see, okay, when the battery is full, okay, let's state here is 0. Now it will be empty. Okay, we have 1. When it will be full again, 0, and etc. 1. Okay, so it is working. Now we can kill everything. Congratulations, you have finished the activity. You have worked with custom messages, custom services. You have created nodes, created publishers, and have worked with service servers and clients. In fact, you have worked with everything we have seen until this point. What is a Ros2 parameter? To understand Ros2 parameters, let's start with the problem. Let's come back to the camera package I used when explaining packages and nodes. Inside this package, we have a camera driver node, and we will focus on this node. So what does a camera driver node do? Well, it is expected to connect to a camera through a hardware interface, for example USB, and then get the images from the camera. Now, inside your node, you will have some variables for settings. For example, the name of the USB device, the FPS you want to apply, and if you want to run your node in a simulation mode or not. Of course, you could have much more settings. So if you want to run your camera and the USB device name is different from the last time, well, you'll have to change that setting inside your code and recompile if needed. If you want to start your camera with 30 FPS instead of 60 FPS, well, you'll have to change your code again. And what if you want to run this node twice, once in simulation mode for a certain camera and once in real mode for another camera? Well, you can see that hard-coding those settings into your code is definitely not a great option. And here come Ros2 parameters. A Ros2 parameter is a configuration value for a node, useful for any kind of setting. So you first need to declare those parameters in your code, and then when you start the node, you set the values. So here, for example, we start the node and give some values for the parameters. Those values will be set in the code so the node can use them. Now, if you want, you can kill the node and start it again with a different FPS value, for example. Or you can start another node with different settings. And the best part is that you didn't touch anything in the code of the node. You don't need to compile the node again, you just need to provide the parameters values at runtime. So, to recap, Ros2 parameters are used to provide settings for your node, and you set their values at runtime. A parameter is specific to a node. It will only live while the node is alive, and two different nodes will have two different sets of parameters values. A Ros2 parameter has a name and a data type. Among the most common types, you can use booleans, integers, doubles, strings, and list of previous data types, etc. Alright, you are now aware of what are Ros2 parameters and why we need them. The first thing you have to do when working with parameters is to declare them from within your node, and that point is very important. I will emphasize this all over the section. So let's get started with parameters. First, I will start here the number publisher node. So that is the node we created in the section on topics. Number publisher. Okay, and let's also start Ros2 from my Python package, the number counter app. So you can work with parameters directly from the terminal with the command line tool Ros2 param. So in this section, I will also teach you how to use this Ros2 param command line tool. If you press tab twice, you can see all the commands, and here we will use Ros param list. Okay, and what is that? So Ros param list will give you the list of nodes. Okay, if you do Ros2 node list, you have the same list here, number counter and number publisher, and for each node, it will give you the list of parameters for this node. So here you can see we didn't declare any parameter, but still we have a parameter use sim time, which is use simulation time for each node. And basically every time you start a node, you automatically have this parameter set by Ros2. So Ros2 param list to get all parameters in your graph, and Ros2 param get a parameter value. So you put the node name first, number, let's say number publisher, and then the name of the parameter. Use simulation type. And what you get here, Boolean value is false. So you will get this message every time, the type, which here is a Boolean, and the value here, which is false. So Ros2 param list with Ros2 param get will allow you to easily find what are the parameters currently running on your application. And the reason I started this number counter here is just so you can see that here we have two nodes with two parameters, but each parameter is private to the node. Okay, so this parameter useInTime is only for the number counter node, and it is totally different from the parameter useInTime for the number publisher node. So if you have a different value here, if you change the value, or if you set the value to true, for example, this will not change the value for that one. So those are two different parameters. As you saw in the previous lecture, you don't have global parameters. Each parameter only exists through the node, and when you kill the node, if I kill number counter and I do Ros2 param list again, then we still have number publisher, but the parameter, this one, from number counter has also disappeared with the node. Okay, so now let's see how to declare a new parameter, because we only have that one. So let's see how we can declare another one. And we will do that directly from the code. So let's go first with Python, and number publisher here, we will modify this file. So we have our node here, and we will declare a new parameter for this node right here in the constructor just after initializing the node. And to do that, we will do self-declare parameter. So you have a function directly from the node class, and we give a name. Let's say test123. Okay, we save the file, and that will declare a new parameter for the node, which name is test123. So let's see what happens when we start the node again, and I will just make sure build packages select my Python. I will compile the Python package again with the symlink installed flag. So after that, we will not need to always compile. So we start the number publisher again, and when I do Ros2 param list, we have test123. Okay, so that here has declared a new parameter for this node, and this node only. So when you are here, you go to the constructor here, you initialize the node, you create it, and just after that, you add one parameter for the node you've created. Okay, and what is the value? Because we haven't set any value, right? So Ros2 param get number publisher with test123, and you have parameter not set. So the parameter, you have two steps. First, you declare it, and then you set the value. Okay, so for now it exists, but it is not defined. It is only declared, and we can actually set the value directly with the Ros2 run command line tool. So for now, you have seen that you can use ros_args with -r, for example, to rename a topic, to rename a service, or to rename a node. And now we just use -p for param to add a new parameter, or I would say to set a parameter's value, which is already declared. So you use ros_args and you put everything after that, but you only need to do that once. So if you do multiple remapping or you add multiple parameters, you only need to do that ros_args once. Okay, so -p and then test123. Make sure that of course the name is the same as the param that you've declared in your code, and let's say the value is 3. So nothing changes here, okay, because we didn't do anything in the code differently. And so the parameter will still be in the list. We get the parameter, and we see integer value is 3. So we have the value here, and you can see the type is now integer. And why integer? Simply because when you set the parameter, Ros2 has detected that it is an integer. So you don't actually set the type by yourself, it is dynamically set. If now I run it again with 3.14, for example, this is a float number, so you will get float or double, it's the same, you will get double value is and the type. Now let's say I put that, so it becomes a string, okay, you will get, okay, so as you can see, if you put a number with that, you will still get double. So it depends how the value is evaluated, okay, you will need to do some tests, and if I do hello, that will be a real string, okay? So when you set a parameter, it will be important to know what will be the type, so then you can use it in your code, but we will see that just a little bit later. So now, let's see if we run that command, okay? We have that command with test123, but this time we don't declare the parameter in our code, okay? So I start the node, I don't declare the parameter, but I try to set the parameter. So we don't have any error, okay? But if I do Ros2 param list, you can see that the parameter is not here. So that's why you have to declare parameter from within your code. If I start it again now, the param is here, and it is also set because we have done that. So, for example, now if I want to add a new parameter, another param, and this will be, let's say, hi. If I want it to appear on the list, I need to declare it here, self-declare another param. So you can declare as many params as you want, okay? And now I start it again. You can see Ros2 param list will give us another param, and it is also set with a value here. You can get it, Ros2 param get number publisher, another param. And you have the value string is high. Okay, and that is for Python, okay? And you will see in C++, it is exactly the same thing. So let's open number publisher. No, this is the Python one in the C++ number publisher. Okay, and here we have done that at the very beginning of the constructor. We will do the same here. And we will simply do this, declare parameter, and put the parameter name inside the parentheses. So the syntax is exactly the same between C++ and Python. So you have seen how to declare parameters and why you need to declare them, otherwise they will not appear and you can't set them. And now let's see how to actually use the parameter from within your code. And first we will do that in Python and then in C++. This lecture, you will see how to actually get and use parameters from within your Python node. So we will work again in the number publisher node, and as you can see in the previous lecture, I have created some test parameters. I have declared some parameters just to test the feature, but I will remove them, and now we will work with parameters that are more meaningful for our application. So what kind of parameters can we use here? If you look at that, we have a number we want to publish, and for now we have hard-coded the value. So if we want to change the number we want to publish, it means that we have to change the code every time, and that is a good candidate for a parameter. So let's actually get this number from parameters, so we can set it directly at runtime. The first thing we need to do is to declare a parameter. So we declare the parameter name, and let's name it number to publish. Okay, so it's quite descriptive. So if you run the node like that, you will have a new parameter, number to publish, but this parameter will not be set. You will need to set it directly by providing an argument with the Ros2 run command line tool. And now that the parameter will be set, how can we get it from the code? You have another function, self get parameter. So get parameter from the node, again, you can declare and get parameter from the node. And what we put here is simply the name of the parameter, number to publish, and this will return a parameter object. So to get the actual value, we will add dot value. So first we declare the parameter, and then we get the parameter, make sure the name is the same here, and dot value to get the value, which here will be an integer, and we have to provide an integer. So that's just 2 lines of code to declare and get a parameter. Now let's run Ros to run my Python package number publisher again like that. So I have already used simly install, okay, so I don't need to compile it again, with Ros as -p number to publish. Okay, make sure it is the same name. Here it's right, okay. And let's say I want to publish 4. So it is started. We can see Ros2 param list. We can see that we have the number to publish, Ros2 param get number publisher, number to publish, and the integer value is 4. So if we do Ros2 topic echo number, what do we get is 4. Great. So let's kill the node and let's start it with 5. And now we get 5. Okay, that's great. So now directly with parameters, instead of changing that every time in the code, you can set any value you want directly by changing that value over there. Okay, and now let's see what happens if you don't set this parameter. And we have an error. Why do we have an error here? So the node has been started, but the error comes from the here message.data, which must be of type integer. And the problem is when we don't set a value, the parameter is declared, but it is undefined, and that actually will be undefined. So when we try to use it, of course, we will get an error in our code. Okay, so it means that you always have to provide a value, or else you will get an error. And here we have another great functionality is that you can simply add a default value. Let's say I put 2 here. So when you declare a parameter, you can use 1 argument or 2 arguments. If you put 2, the second one will be the default value. So what it means is that when you declare the parameter, it is not undefined anymore, it is set to 2. So I can start again without any parameter, and it will work, and we still have data 2 here published on the topic. If I start it with 5, so this will override the default value, and we will have data 5 here. Okay. So it is always a good practice to put a default value for your parameters, because you can't really trust what's on the outside. Okay, you know what you do in your node, but you don't know how the node will be launched. So if you forget to put the parameter, then you will get an error, and you don't want to get that many errors. So you will set a default value. If you don't want to set a default value, you can of course make it mandatory to provide a value at runtime. Okay, but here we will choose to put default value. So if you don't set any number, the number will be 2. And while we are still on this node here, there is something else we can easily put as a parameter, is the frequency at which we publish the number. Here the frequency is fixed, it's 1 Hertz. So here it's 1 second, okay, the period of 1 second, which means 1 Hertz. Maybe we also want to change that frequency. If I want to publish number 3 at 5 Hertz, then, okay, I have the parameter for the number to publish, but I still need to change that value over there. So let's declare another parameter, and that will be publish frequency. Okay, and we will put a default value right now, which will be, let's say 1 Hertz, okay. And we will get the parameter here and set it here. So we create a new attribute. For example, let's say publish frequency. So here you can put it as a member of the class or not. It doesn't matter. We'll just use it here. And that you will use get. So self get parameter publish frequency. So if you don't set manually the parameter, you will have 1.0. Okay, and now we can change the value here, but actually we will not directly put the frequency because the argument expected here is not the frequency, it's the period. So the period is simply the inverse of the frequency. Publish frequency. I will do some auto formatting. Okay, so now if you choose a frequency, that will automatically change the period for the timer. So let's check that actually. I will start. So if I just start it like that, we have a problem because of course you need to write value. Okay, as you can see here, the type is parameter. So when you do get parameter, you get a parameter object, and you need to value. This is a frequent error you will get at the beginning to forget the value attribute. So we start again, and as you can see, it is publishing data at 1 Hz. And if you want to actually check what is the frequency, you've already seen that before. You can do Ros2 topic HZ for Hertz and number that will listen to the topic and print the frequency. And what? Okay. So average rate 1 Hz. Okay, so that is what we have here with the default value. And now I will start it again with dash p. Okay, you still have only one Ros arg, but you have multiple dash p for multiple parameters. Dash p number to publish and publish frequency. Let's say 4.5 Hz. Okay, just random. And okay, as you can see now, it's going much faster. Okay, and if I monitor with Ros topic Hertz, great, we find the 4.5 Hz here. So well, that's pretty much it. Okay, you first need to declare parameters. It's better to put a default value so you can avoid some errors at runtime, and then you simply use get parameter with value to get the value, and then you do whatever you want with the value. It just depends on your application. And now let's see how to get and use parameters directly from your C++ nodes. So that is what we did with the Python node with the number publisher, and we'll do the exact same thing but with C++. So you will see that will be really similar. So we go to the number publisher CPP. Okay, we already have one declaration here that we used to test in the declaration lecture. I will remove that, and we will do the same. We will declare the parameter for the number to publish. Okay, and so if we run this node here, of course we will have in the list number to publish, which will be not set. Okay, so I will directly add a default value. Okay, so we will not have an error if we don't set the parameter when we declare it, and if we try to get and use it. So now I want to get this parameter and put it inside the number here, number of the class. So what I will do is number will be this get parameter. Okay, you have a get parameter function inside the node, and I will put the name, which is number to publish. Okay, and we will get a parameter object. So what we need to do is we need to get the value. Okay, and in Python, if you look at Python, we just did value because in Python the type is dynamic. So number will be an integer if this is an integer, number will be a string if this is a string, etc. In C++, you can't do that. Number is already an integer. So you can't just get the parameter because the type is dynamic. So you need to cast directly, and you see you have as bool, array, as double. So for every type of parameter, you have a function to cast directly for your C++ code. So here we expect an integer, so as int. Okay, and now that is correct. What we can do is remove this, okay, because we are setting number here, but we are setting the number also here in constructor, so this becomes irrelevant, so we can remove that. Okay, and now we have our number, which can be set from the outside at runtime. Let's also declare parameter for the publish frequency, and by default this will be 1 also. And I will create here double publish frequency. You can put it here as a member of the class if you want. Just for this example, I will not do that. And this get parameter publish frequency, and we need to cast it as double. This is a double, so we cast it as a double. And now we will use this publish frequency right here for the first argument of the create wall timer function. So we need to give a period. Okay, so we need to do 1 divided by the publish frequency. And here with SD chronos seconds, we can't, as you can see, we have to give an integer. We can't give a double. So what we will do here instead is to use milliseconds, and we will simply multiply the result by 1000. Okay, so we get a better precision. You will see. So 1.0 divided by publish frequency. Okay, we will cast as an int here, and we will simply multiply by 1000. So if the frequency is 1, then the result here will be 1000. 1000 milliseconds is 1 second. Okay, and we will have a precision up to 3 digits after 0. Great. So now we can launch the node, and actually we will build the package again because, well, this is C++. Packages, select my C++ package. So run my C++ package with number publisher. If I just launch it like that, so if we listen to the number topic, we have data2, which is published at 1 Hz. Ros2 param list will give us the list. Okay, with the 2. If you get them with Ros2 param get, you will see the current value. So let's do that. Ros2 param get number publisher with publish frequency, for example. We have 1.0, which is double, and this is directly coming from the default value. And now I will add some parameters. So Ros args -p number. Okay, you can put the parameters in any order you want. Okay, it doesn't matter. If I do publish frequency first, it's the same frequency. Let's put 6 Hz, and then I can do number to publish. Let's publish 7, and we have an error. Yes, because I forgot the -p. Okay, that is the error you will have if you forget to put -p. You need to put -p before any parameter. And you have also another error this time here because publish frequency. If you do that, As you can see, the type will be dynamically set, and if you do 6 like that, if you choose 6, it will be set as an integer. And what you do here is you try to get it as a double, so it will not automatically cast it from integer to double. You need to have the exact same type. So if I want 6, I need to put 6.0. And now it is working. If I do publish frequency, I see 6, and we can see here it's going much faster. We have data 7, and let's do Ros2 topic hz number. We should have the result, which is 6. Okay, you can see the average rate is 6 Hz. And one error I want to show you also, okay, if you try to get a parameter, but you haven't declared it before in your code, so I will build a package again. So this is independent whether you set the parameter here or not, because if it is not declared, you can set any parameter you want here, it will not be on the list. So if I just start it, I will get an error because you have accessibility exception, parameter not declared exception, and that is what you will get if you try to use get parameter for something that has not been declared before. So you need to declare parameters again. That is super important. So now I can compile and it will work again. This is the solution of the previous activity where you need to set some parameters in the nodes that you've already created before. So first I will do the robot news parameter, and then we will go to the LED panel node. So in the robot news station. Okay, robot news station node, we have the name of the node here, which is hard-coded, and we will want to change that, and we will put a parameter for it. So first let's declare the parameter, self declare parameter with the name, let's say robot name. Okay, that is the parameter name, and we will put a default value, and we will keep the same value for default. Okay, so we have the default value, and then we can directly get the robot name, self get parameter from the parameter robot name, and of course don't forget to add value at the end. Okay, so well, that's it, just those two lines. So you declare the parameter with a default value, and then you get the parameter value. And now if we run this, so I have used a symlink install so that I don't need to install the node again. So Ros2 run my Python package robot news station. If I don't put any parameter, let's see, Ros2 topic echo robot news, and we have hi, this is C3PO. Okay, I will keep it running. Okay, I can see Ros2 param list, so you can see the parameter is here, and you can get the parameter also. Now if I start the node again, ros -p with robot name, and let's use Giscard, and we press enter, and hi, this is Giscard from the robot news station. Great. If you want to add space, for example, Giscard 2, then you can do that simply, and you have hi, this is Giscard 2. Okay, and if you get the list, Ros2 param get robot news station robot name, you get the value that you set right here, okay, which will override the default value. And now that is great because you can start multiple robot news station nodes which are publishing different values over this robot news topic. Okay, so I will continue with that one. Okay, we have robot news station, and I will start another one. I will source this, I'm not sure. Okay, Ros2 run my Python package robot news station ros add. You can start with a different parameter, and also, and that is important, you can just start two nodes with the same name. Okay, so here we will also need to rename the node, so you can do that. Node, let's say news, let's say another news station, you get dash p. So here we rename the node, and we add a parameter robot name, another robot. Okay, and you can see here we receive both messages from the two publishers. Ros2 param list, only one L is better. So here you see the two nodes on the graph with their parameters, and as you can see, the parameter here is quite different from this one. Ros2 param get another news station with robot name. Okay, and Ros2 param get robot news station robot name. Those two values are different. Okay, so you can clearly see that one parameter is already private to the node. And let's quickly see the C++ side for the robot news station. Okay, well, that is the same. Okay, we declare the parameter, same name, default value, and we get the parameter, and we use as string because robot name is an std string, and we expect a string, of course. At the LED panel node, here we have let states, which is an array we have fixed here. But let's say you want to start this node with a different configuration for your LED. Maybe you have 4 LEDs, maybe 5, maybe some LEDs are already powered on, etc. So we will again here add a parameter, self-declare parameter, which will be LED state. So that will be the initial LED state, and by default we will keep this value. Okay, and now when we set the LED states, we will do self get parameter LED states value. Okay, I will do that, and that's pretty much it. So we can now go back here, Ros2 run my Python package with LED panel. Let's put some parameter, so LED states, and we simply put an array. Let's put 0, 0, and then 0, and then maybe 1 and 1. So we have 5 LEDs. The first 3 ones will be set as 0 at the beginning, and the last 2 ones will be set at 1. And if I do Ros2 topic echo LED state, we have, okay, we need to wait a little bit, and we have the new LED states. So you have changed the number of LEDs and the initial values. Okay, great. And you can also now use the service to change any LED you want here, and you can send a LED number from 1 to 5. It will work. Okay, so that is quite simple. And now let's check the C++1 that I have already written here. You also have those 2 lines. Okay, so I have removed here the initialization, which will happen here. So that is the way to write. You can write an std vector, okay, like that as a default parameter value. And here you have get parameter, and you have as integer array. Okay, so I told you have a cast function for any parameter type supported in Ros2. And as more practice, one thing maybe you can do here as an additional step for the LED states parameter is to validate them. Okay, because for now we just get the parameters value and we assume that they are correct every time. Okay, but it's just the same thing as with the set LED service. You don't know what will arrive here, what kind of value you will get. So maybe if I do that, if I send 4 here, okay, as a value, we will get the value 4. And that is not correct. So we have checked the value in the set LED service. You may also want to check it here. And if the value is not correct, you can, well, it depends on your application. You can make the application fail, return, you can set the default value, etc., etc. And if you want, you can continue to browse the different nodes that we have here. And when applicable, you can maybe put some parameters. For example, here again, we have a period that maybe we can use with a parameter. What is a Ros2 launch file? So let's start with the problem. Let's take the camera driver node we used to explain Ros2 parameters. You start this node for one camera with 3 parameters: the USB device name, the FPS, and a simulation mode flag. Note that you also remap the name of the node here. Now you want to add another camera driver node for another camera on your robot. So you start a new camera driver node in another terminal. And of course, you rename the node and set all parameters values. And oh, there is a third camera on your robot. So that's another node in another terminal. And that's not all. Now you want to add a robot news station node with 1 parameter this time. Your application is not complete yet. You add 2 LED panel nodes with name remapping and 1 parameter each. And so on. You continue to add nodes to run your application. Each node in its own terminal with all the options required to name the node, set parameters, etc. And as you can see, that is a real mess. And it will take you forever to launch that every time. Plus, with all that configuration, you may have some mistakes and it will take more time to debug. So at this point, you might want to run a script to start everything automatically and not manually. That way, you can truly scale your application. Well, that's exactly what a launch file does. Here, I have put all the nodes and configuration inside a launch file. A launch file will allow you to start everything from one single file. That way, you will be able to quickly launch your application and to create different launch files for different startup nodes of your robot. It's not uncommon for a robot to have something like 10 nodes and maybe 200 or more parameters. Without using launch files, it would be impossible to start such a robot application. Now that you understand what is the purpose of a launch file, let's see how to actually create one for your Ros2 application. So we will create a launch file for the number app, which is basically the number publisher node plus the number counter node, so that we can launch both nodes with any configuration we want from only one file. So let's go inside our source directory in the Ros2 workspace, and for now we have 3 packages. So where will we write the launch file? And in fact, we will create a new package just for launch file. So Ros2 package create my robot bring. Okay, so first, why do we create a new package? Well, for kind of the same reason as for the interfaces package, because this will be easier if you have all your launch files inside one package only, and actually the launch files will pick some nodes from many different packages, so it will be easier to centralize them in one package, and also it will reduce the number of dependencies between your packages, because well, like messages and services, you can create them basically in any package you want. For launch files, you can also create a launch file in any package you want, but this will add dependencies between packages that you don't necessarily want. And then why do we name the package my robot bringup? This is not just random, this is something that is quite often used by the Ros community. You put the name of your robot and then bringup. So if you start using that kind of convention, it will be easier for you to work with other people's code, and other people will also find it easier to work with your code. So we create the package my robot bringup. We don't specify any build type or dependency, and we have a new package. Let's go inside that package. So if you remember, when we don't specify a build type, this will automatically select the element CMake build type, which is also the same as for C++ package. And we will remove the include directory, remove the source directory, and create a launch directory. So in this package, we will have the cmakelist.txt launch folder and package.xml. Let's see our package here. So for now, we don't have any launch file, but we will first configure the package. So in package.xml, you still have the information tags that you can fill if you release the package. And then we don't need to make any addition for now. We will, of course, need to add some dependencies for other packages once we create a launch file. And in the cmakelist.txt, okay, I will actually remove that and that until here. We will need to provide the instruction to install the launch folder. So we will not install every launch file one by one. Okay, we will directly install the complete launch folder, and everything under that folder will be automatically installed. So install with directory. So we select the directory launch, which is that directory from this package, and the destination will be share with package name, project name. Okay, so what we are telling the compiler here is to install the directory launch inside the share my robot bringup folder, which will be inside the install folder of your Ros2 workspace. All right, so the setup for launch file is now finished. So you just create a new package with a launch folder, and you install that launch folder from the cmakelist.txt. And now let's create our first launch file. Inside launch folder, we will create number app.launch.py. So launch files are Python files. Okay, we will write the launch file in Python. So you have a .py, and you can use that also as a convention .launch.py. So you know it is a launch file. We will make it executable because we will use the symlink install flag with Golcon build, and so that will be the same as for Node, as for Python Node. Once you use Golcon build with symlink install, after that you don't need to actually build every time. You can simply change your code and execute again, and you will have the new changes. So let's edit the file. Here I will first write the minimal code you need for your launch file. So a launch file is not a typical Python file. You don't write a main function or a complete program. In fact, you just need to do one thing, is to create a function named generate launch description. Okay, and the name should be exactly generate launch description, like that. Because when you install the launch file, the launch functionality will actually create a new program which will take that function to launch your application. But if it doesn't find that name exactly, then nothing will happen. So what you need to do inside that is to create a launch description, and you will import it from launch import launch description. You create the object launch description, like that, and that is the first line of your function, and the last line will be return launch description. So there you have your template for every launch file, and this is actually the minimal launch file you can write. So now, before we actually start some nodes from there, let's see how we can start it. With Golcon build packages select, we will only build my robot bringup package, and also use the symlink install. Okay, in that terminal we'll source the bash rc. And now how to launch the launch file. So with Node, you have seen you can use Ros2 run. Well, for launch file, you can use Ros2 launch. That is another command line tool directly from Ros2. And then you will need to provide the name of the package, my robot bringup. You can press tab also for auto completion. And let's simply put the name of the launch file. You start it, and it's working, and of course it will return because we don't have any node spinning here. So now let's add a node inside our launch file. So to create a node, we need to import the node object from launch ros.actions import node. Okay, that is a different package here. And you can create a node, let's name it number publisher node, with the node constructor, and that will take multiple arguments here. We will write the package and the executable. Okay, that is the minimum thing you need to put here. So the package name is my Python package. We can use the Python or the C++ one, okay, it doesn't matter because we have the same for both. My Python package, and the executable name is number publisher. So if you are not sure, you can check in the setup.py here. We have number publisher, which is the executable here. So that is the minimal code to start a node from a launch file. You just need package and executable. It's just like you start this with Ros2 run, okay? Both are the same arguments. So what you can do now that you have this node object is to do launch description, add action, and number publisher node. So for launching a node, you create a node object and you add it to the launch description, right? And now we have our node number publisher node. Let's add counter node and simply create it with package, which is, okay, let's use the C++ package executable number counter. So let's actually name it number counter node, and let's add it here, add action number counter node. Okay, great, so we are launching two nodes. And as you can see, we can choose from which package we want to launch them. Here, for the first one, I launch a node from my Python package, and for the second one, I launch a node from my C++ package. So, well, actually, I will save the file, and before we launch that, we will add some dependencies here in package.xml, okay, right here, because in this package, we need those two packages, so we will provide some dependency tag, and we will not use depend, we will use exec depend. Okay, the depend tag will actually have inside the exec depend and also a build depend. Here we don't need the build depend tag. Okay, we just need exec, which means execution. So it means we need the dependency when we execute the file. So my Python package exec depend and another exec depend for my CPP package. Okay, and now let's start the launch file again. So I have not built it again because I used symlink install and the launch file was already an executable file. And as you can see here, it's quite different. We have number publisher node with one means process one, so process started with PID, you have the PID for this process. Then you have number counter node with 2 because this is process number 2 from the launch file. Okay, and then you have the logs from the different nodes you are launching. Okay, and as you can see here, the program didn't exit because some nodes are spinning. If here I do Ros2 node list, you can see we have the 2 nodes we have started. So with just one launch file, we are able to start multiple nodes at the same time. And if I kill this, it will basically try to kill all the nodes, like if you run the nodes in multiple terminals, like if you press Ctrl+C in every terminal. And I can start it again, simply like that. Write a launch file and start it to start an entire application with multiple nodes coming from different packages. But now let's see how you can customize this application. You have seen in this course already how to add some parameters to your node, how to rename the node, how to remap the topic, etc. And you have seen how to do that from the command line tools with Ros2 run. But you can also do that in a launch file. Okay, so let's see how to do. First, we will rename nodes. Okay, to rename nodes, you simply have to add a new argument here, name. Okay, and the name here by default will be number publisher. Let's name the node my number publisher. And let's name this one, name my number counter. So we can launch the launch file again. And as you can see, we have my number counter and my number publisher here. And you can see the nodes have been renamed. Okay, you just need to add this name along with package executable. Okay, now how to remap the topic? We have Ros2 topic list. So we have the number topic between number publisher and number counter, and we have the number count topic, which is coming out the number counter node. So let's remap that. We will use remapping. Okay, and remappings, you need to give an array of tuples. So we will remap first the number topic to my number. And of course, if we do that, then the number publisher node will publish on my number topic, which is a different topic from number. So we also need to remap here if we want it to work. So we will also add number and my number. Actually, we can also remap the number count. If we want, let's do that. My number count. Okay. And because here we have the same remapping as for this node, actually we can create a tuple outside. Let's say remap number topic, and actually put a tuple here. And now we will simply put remap number topic right here. So that is the magic of launch files. Okay, you can add a remap rule here, and then you can apply it to any node you want. And if I just change the rule here, it will apply to all the nodes. So let's save it and let's actually start the launch file again. So we still have nodes which are my number counter and my number publisher, and topic list we have my number and my number count. If I do Ros2 topic echo my number count, then we should have the correct counter. So it means that everything is working. So we have renaming for nodes, for topics. Well, if you want to rename a service, that is exactly the same thing. You put a new tuple with the service name and the new service name. And now we can also add parameters. You add another argument here, parameters, and you need to give an array. This time it is not a tuple, this time it will be with a dictionary. So in the, let's see what we get inside the number publisher, we have 2 parameters, number to publish and publish frequency. So actually we will set them directly from the launch file. So number to publish. Let's say we want to publish 4, and then we have publish frequency. And let's say we want to publish at 5 Hz. Okay, now we can start again. And we still have the same topic names. Now if I do equal minor count, you can see that it's growing by 4 every time, and the publish frequency is quite higher. You can check with Ros2 topic HZ number, actually it will be my number count, to see that it is publishing at 5 Hz. So you have seen how to rename nodes, remap topics, services, and add parameters. And well, because you will write this function with Python, you have infinite possibilities with what you can do. Okay, you can add conditions, you can add loops, you can add any logic you want to start your node and everything inside your node. So with just one launch file, you can completely customize your application. And as you can see here, we just need to do that. Okay, that is just one command line to start your entire application. This is the solution for the activity I gave you in the previous lecture. So that is what you should get at the end of this activity. We have 5 different nodes, which are all robot news stations, which are publishing on your robot news topic, and then the smartphone node will get everything from those nodes. And as you can see, we have named the different nodes with different robot names. So let's create the launch file to do that. So actually, we don't need to write any code in any nodes because they already all exist. So we just need to create a launch file to launch them. So in the source, we have my robot bring up, and we'll go inside the launch folder and create, let's say, radio.launch.py. Okay, we can now edit the file. So in my robot bringup, radio.launch.py, and we will use nodes from those packages that we already added in the package.xml with exec depend. So here from launch, import launch description, we need to create a function generate launch description. Okay, inside that we will create a launch description object and return that object. Okay, we have the structure. Now we will add nodes. So from launch Ros.actions import node. Okay, so let's first start with one node. We will create that node, robot news station Giscard. So first I will write one robot news station node and the smartphone node so we can test the communication. And finally we'll add the 4 other nodes. So for example, station 1, we can say node from package my Python package, for example. You have the executable, which is robot news station. So that will never change because it's what we defined from the package directly. So we need to use that. And then let's rename it. So let's rename it robot news station Giscard. Robot news station Giscard. Okay. And actually, we have a parameter containing the robot name that we will fill here. Robot name Giscard. Okay, so that is our robot station node. We have now the smartphone node. Smartphone will be node with package my, let's launch the C++ one, executable, which will be smartphone. And actually, we don't need to change the name because the default one is smartphone. But you can still, if you want to use name smartphone, just to be sure. So we add the add action. We add the node station 1 and the node add action smartphone. Great. So let's first try that. Qualcomm build packages select with my robot bring up, and let's use symlink install. Okay, now source that terminal Ros2 launch, name of the package, my robot bring up, name of the launch file, which will be radio launch.py, and we have, okay, as you can see, we have some logs here because we are starting the robot news station node and the smartphone node. And as you can see, the smartphone is printing something on the screen, so you will have the logs from every node on your launch file. So we can see, hi, this is Giscard from the robot news station. Okay, and okay, let's start it again and let's check Ros2 node list. We have robot news station Giscard and Ros2. So the name of the topic is the same, robot news. Okay, we haven't changed that. We have just changed the name of that node plus the name of the log of the message we sent. And now let's go back here and how to add all those 4 nodes here. So the first option is just to start station 2, station 3, etc. and add them here. But actually we will use a for loop here and you will see that will be much easier and faster. So first let's put the robot names into an array. Okay, we have Giscard, and then we have BB8 Daniel 8. We have gender and gender and C3PO. So we have our 5 robot names here. I will create an array robot news station nodes. Okay, and we will add nodes with a for loop for name in robot names. So for each name here, we will create a node. So robot news station nodes append to create something new inside the array, and simply create a node here. Package will be, let's choose the Python package. The executable will be, of course, robot news station. And then we will change the name, and the name will be robot news station plus the name of the robot. And actually we will do, so the name is here, we will do name.lower. So this is a string, we can use lower, which will put the name in lowercase, okay? Because we always use lowercase for node names. And finally we can add the parameter simply with robot name and the name. Okay, so here we have created 5 nodes. I will remove that one, so I will also remove that. And now how to add all the nodes in the launch description? Well, let's use another for loop. For node in robot news station nodes, we will do launch description add action node. Great, and that's it. So you can see we have 28 lines of code, and we are starting 5 different nodes here with different names and parameters, plus a 6th node that will listen to everything from the topic robot news. So with that example, you can truly see the power of launch files and why you definitely need to use them in your application. So finally, if we start it here, you can see, okay, let's go here. You can see we have different processes. We have 6 processes that were launched, okay, 5 robot news station executables and 1 smartphone executable. And now you can see that the smartphone node receives a lot of different messages from each robot news. And if we Ros2 node list, we have the different nodes. Actually, this is not exactly what we want. I will add another underscore here, and let's start it again. And now that is correct. So if I do activity graph, we have the correct setup. I will use that here. Okay, we have all the different nodes publishing on robot news, and the smartphone is subscribing to the topic and is receiving all the data. Here is the final result you will get at the end of this project with TurtleSim. So I will start the launch file, which launches everything in the application, and you will do this launch file in the last step of the project. Okay, to launch everything. So we have 3 nodes here, a TurtleSim window, a node to control the turtle, and a node to spawn turtles. And as you can see, the turtle, the main turtle, will try to catch every new turtle which is on the screen, and when the turtle has been caught, it will disappear, and the main turtle will start to go to another turtle. this is the first step of the solution for the TurtleSim mini project. So first of all, we will create a controller node to actually control what we call the master turtle, okay, which is the first turtle we will have with Ros2 run TurtleSim node. So if you run that, so you have a turtle here on the screen, and we will want this turtle to catch all the other turtles that are spawning. So first, we need to give an instruction for this turtle on how to go to a given target point. And that's what we do right now. So I'll just resize that. Okay, and so how can we actually control this turtle? As you can see, we have different topics here. And for this turtle, which is named turtle1, okay, spawning turtle1 here, we have a topic named command velocity, which is a subscriber here. So we need to publish a command velocity to move the turtle. And we have a turtle1 pose topic, which here is the current pose of the turtle. So if I do Ros2 topic echo pose turtle1 pose, as you can see, we get the current position here. You have x, y, and theta with also the velocity. So we will use that information so we can know what command we should give to the turtle. So let's create our turtle. I will go to the source folder of the workspace. Let's create our turtle controller. And first, I will create a new package. Okay, Ros2 package create. Let's call it TurtleSim catch them all. And I will do the solution in Python. You can also find the C++ solution. At the end of the section, you can download the complete code. So let's specify build type element Python, and we will specify any dependency directly inside the package. So we have a new package here. Okay, so we will write the code inside this folder. As you can see, this folder has the same name as TurtleSim catch them all package. Okay, and let's create our first node inside that package. Here, touch turtle controller, and let's make it executable. Okay, so we will control this turtle. We will not create a new turtle. Okay, we will use turtle1 as the master turtle. So we have our file here, and let's use the template we have. Okay, and this will be turtle controller node. Let's name it turtle controller. So in the package.xml here, we will need to specify depend rclpy because we will use rclpy. Okay, so if you don't provide the dependency with Ros2 package create, you have to put it manually, but it's just the same thing. Here, so we have rclpy. What we will do now is we will need to first subscribe to the turtle1 pose, Ros2 topic info turtle1 pose, which is of type TurtleSim MSG pose. Let's see what we get here in face show with pose, and that is what we saw here. We have all data fields are floats 32 with x, y, and theta, and we will be mainly interested in that. So in order to create a subscriber for that, we will need to actually from turtlesim.msg import pose. And as we use the TurtleSim package, we also need to add it here, depend TurtleSim. Now we can create a subscriber. So let's create a callback function first. Callback turtle pose. We receive message, and what we will do is we will create a pose object which is known at the beginning, and then we do self pose is equal to the message. So here I will directly use the message, which is an object pose. Okay, I will directly use that to store the pose in our class. So whenever we receive a pose, the pose of the class is directly updated. And now we create the subscriber pose subscriber, which will be create subscription with pose name of the topic. So the name of the topic is that one here. And actually, we don't need to add the first slash, it will be added automatically. We specify the callback turtle pose, and a queue size. Let's format this. Okay, so we got our subscriber, and the pose will automatically be updated whenever a new message arrives. Now we create a publisher for this topic. So Ros2 topic info with that. And this is a twist message from the geometry messages package. Let's see what we have inside. Face show twist. So you already saw that one before. We have a vector 3 for the linear velocity and another vector 3 for the angular velocity. If you do Ros2 in face show with, so it will be in the geometry SGS folder package, because there is no package name in front of the vector 3, and we have float 64 x, y, and z. So we need to include first that inside our package, inside the node, from geometry msgs.msg import twist. So that TurtleSim we already installed it before. The geometry messages package, you should already have it, but just know that if you don't have the, if you see here that you with Ros2 topic info that you don't have the package, you can simply install it with here it will be Ros dash name of the distribution dash name of the package. Okay, we have that. So as we use geometry messages package, we will add another depend tag here. Okay, and that's it. Now we create a publisher to publish on that command velocity. So self command vel publisher, self create publisher with the type twist, with the topic name, which is that one command vel and a queue size. Okay, so we have the correct subscriber and the correct publisher. Now we will add a control loop to actually control the turtle so we can make it move. So here let's create a new function, def control loop, and we will add a timer, control loop timer, self create timer, and here we will choose a quite high frequency. I will choose 100 Hertz, so that will be 0.01 second for the period, self control loop. So basically that we call that function at 100 Hertz. And that is something that you will quite often need to do in your program. For example, if you need to create a hardware driver to monitor a sensor, then you can create a timer with a function, and then in the function you will, for example, if it's a temperature sensor, you will read the temperature, and maybe you can publish it or store it inside the class. And you can also use that for a control loop here. What we will do in the control loop, we will simply check what is the target we want. So if we want to go there, we know we want to go there, then we'll check where we are currently, so we are here, and then we will compute what we need to do in order to go there, and we will send a command for the velocity on that topic. Okay, so let's see how to do that. First thing is that we will do a check if self pose is known. What we do is we return. So we don't do anything in the control loop unless we have a pose that came from the turtle1 pose topic. Okay, because to control the robot we need to know the current pose, and we also need to know the target we want to reach. So the target we want to reach, we will have that later in a later step when we have the coordinates for all the turtles that are spawned. But for now I will create a temporary here. Let's say target x, and which will be let's say 8, and target y 3 4. So that will be a temporary target that we can use to test our control loop, and once we know it is working, then we can dynamically change the target to the target of the other turtles. And just here on this screen, the coordinates, this point is 0 0, okay, and then you have x here, which goes until something like 11, and here you have y, which also goes to 11. So we will choose 8 and 4, which means turtle should go somewhere here. Okay, so that is our target for this step. So what I will do here has not much to do with Ros itself. It is more dealing with how to write some control software for a robot in general. So the first thing we will do is to compute the distance. So let's say our target is here. We need to compute the distance and get the distance here, x on the x-axis and the distance on the y-axis. So how to compute the distance between the turtle here and the target point here? I will make it very simple here. So you have turtle and target point. Now what you have here, so you have a rectangle triangle. Okay, the distance x is this size, the distance y is this size, and now you also want to compute that distance, so we will use the Pythagorean theorem. You can Google it if you want more info about it, but this is quite basic, and I guess most of you already saw that in high school. To get the distance on the x-axis, we will do the target x minus the pose x. Okay, in the pose message we have x coordinate, the x field right here that we are using here, and the distance on the y-axis, similar, target y minus pose y. Okay, and now to get the distance directly going from there to there, actually we will use the math module. So let's import it here, math module. So math is square root of distance x times distance x plus distance y times distance y. Okay, so we have distance x, y, and the distance, the direct distance. And now what we will do is we will create a twist message that we will fill with velocities. So we create the message here, then we will do some stuff here, computation, and then we will publish with self command velocity publisher, publish message. Okay, and now let's do the stuff to actually compute what we need to send on this twist message. So we will not need to fill all the linear and angular fields here. Basically, we only need to provide one linear speed and one angular speed. So the linear speed will be x, because the linear speed will always be with the same orientation as the turtle, and then to make the turtle move, we will change the velocity on the z angular speed. So what we will do here, if distance is greater than, let's say, 0.5, so we need to actually tell if the turtle has reached the target or not. And I will not say here that the turtle has reached the target when the coordinates are exactly the same, okay? We will add a kind of a tolerance, so if the point is here, then if the turtle is just a little bit here, we will say that the goal has been reached, okay? It's like in real life, you may set a tolerance, for example, to say, yes, the robot has reached the target point. So what we will say is that if the distance is still greater than 0.5 in the scale of this window, then the target has not been reached. So we need to give a command. And if the target has been reached, what we do? We use message linear x 0.0 and message angular z 0.0. So in the case where we arrived, we simply send a message with 0 velocity, which means we want the turtle to stop. And here, this is the most important case. So first, the position. We will do message linear x is equal to distance. So basically, we will implement a very simplified P controller. We will not use the complete PID. And well, I will not go too much into details here because this is about automation. So it is with robotics, of course, but here the point is to work with Ros. So if you are not really familiar with automation, well, you can continue to work on automation after this course. And here, very basically, what I do with this P controller is that I check the delta, the error. So here the distance is the difference between the target and the current point. And then I simply give the distance, so the difference, as a comment, okay? So that is for the position and then the orientation. So to compute the angle we want, here we have the turtle and the goal, okay? And that is angle 0 on this window, okay? So if you have this orientation means 0, and then you can loop around that circle here. And for example, here you have 90 degrees, 180, etc. and 360 becomes 0 again. So that in blue here is the current angle of the turtle. So that we have directly from the pose object, okay? Which is what the turtle sim node gives us. And now what we want to compute here is that angle right here, which is the angle we need from the turtle to the target point. And how to compute that angle? Well, we still have our rectangle triangle here with the distance x and distance y, which we already computed. And we simply can say that the angle here, so you have, this is the 0 angle. So the angle here, right here, the tangent of that angle is the opposite, which is the distance y divided by the adjacent distance x. So we have the tangent of that angle, and what we'll do is simply compute the arc tangent to get the actual angle. So I will create a variable named goal theta, which will be math a10 to get the arc tangent of the distance y and distance x, which we computed here. Okay, we have the goal theta, and now simply compute the diff to feed the controller. Goal theta minus self pose theta. Okay, so here we had, with the distance, we had the difference for the linear axis, and now we have, with this, we have difference for the angular axis. So what we can do is, message angular z is the difference. And actually what I will do first is to normalize the angle, because if you don't do that, you may have some weird behavior if you go to the edge of the trigonometry circle. So if this is more than pi, we will remove 2 pi. And also if this is lower than minus pi, we will add 2 pi. Okay, and what we can add here, I will multiply this by 2, and I will multiply this by 6, okay? And why I did that, simply because I have already tested, okay? And I found that you can multiply by 2 here and multiply by 6 here, and the behavior will be better. So when you create a P controller, you feed the controller, so you send the next value, which will be the difference, okay? And you can also add some factors, which basically how to find the factors is just by tuning the controller. And how to tune the controller, you have many methods, but here you can just simply observe what you get and modify the factor to get a better result. So if you want, you can not put this and see what it does, and then you can increase or decrease the value to see the behavior. Okay, so the control loop is finished now. If you don't really understand that, it's a good point that you can work on after this course. Okay, you can work more on control loop and automation. So what I will do, I will check if everything is correct. Yes. Okay, so we call the control loop at 100 Hz, and it means that at 100 Hz, we check what is the difference between the target pose and the current pose, and we send a velocity here directly to the command vel topic. So let's save this. Let's add it here to install it. Turtle sim. Let's call it turtle controller. Actually, this is from turtle sim catch. Then all dot turtle controller main function. Okay, I will compile it here. So let's go into the Ros2 workspace and click on build with packages select. And let's choose turtle sim catch demo with symlink install. Okay, so the first thing we need to do is to launch the turtle sim node, okay, because this new node, the turtle sim controller, relies on that. So make sure you have first started turtle sim node in one terminal. And now on that terminal, I will source the bash rc and launch Ros2 run turtle sim. So we have turtle sim, which is the global installed package, and that is our new custom package. I will start turtle sim controller node. Okay, and we see that the turtle has just moved to that point. So now if you want, you can simply use different values here. Let's do let's invest that for an 8. Let's actually relaunch the controller. So we don't kill the turtle, we simply relaunch the controller. And you can see the turtle will start from this point and go to that point, and the trajectory is quite smooth here, okay? And that is because we have the tuning here. Okay, we send the difference, and with a little bit of tuning, it looks good. And that is the end of the first step. This is the step 2 of the solution for the mini project on turtle sim. So in step 1, you have created a turtle controller so that your turtle can actually go from its current pose to a target pose. Now what we'll do is we'll create a turtle spawner node that will spawn turtles everywhere on the screen at a given rate. So this step is completely independent from the last one. Okay, actually, if you did step 2 before step 1, it's okay. So I will kill everything here. Let's clean that, and let's go Ros2 workspace in the source directory in the turtle catch them all package, and let's create a new file, turtle spawner, chmod plus x to make it executable, spawner, and now let's edit the file right here. I will use the template again that I have here. Okay, template, and let's close that. So turtle spawner, here turtle spawner. Okay, and now how do we spawn the turtles? So we will again use the turtle sim node. So we'll see what interface we have to spawn turtles. If we do Ros2 service list, we have a service here, right here. This will spawn a new turtle on the screen. So that is what we will use. We will here create a client, okay, to call this. We will not just use spawn in the terminal like we did before. Ros2 service type spawn, so you know what you need to give. And you have a spawn service inside the turtle sim package. Ros2 interface show. Let's show what we have here. And we have, okay, we have 3 float, x, y, and theta, which are the coordinates of the turtle on screen, and an optional name. So you can provide a name. If you don't provide it, a unique name will be created and returned, and you get a response, which is the name of the turtle. Here, if the turtle was successfully spawned, you will get the name. If you have an error, for example, you try to spawn a new turtle with a name that already exists, then the string will be empty, and that's how we know there is an error from the turtle sim node. So let's include that from turtle sim srv import spawn, and we'll be able to create a client for spawning turtles. So to do that, I will use the template we have for clients inside OOP code, and let's go in, for example, add to int client here. Okay, I will get the callback plus the call server functions. I will copy that and paste it here. Okay, so we have the 2 functions. Of course, now we need to modify them. I will also, I'm going to forget it later, from function tool import partial, because we will use partial here. So instead of calling the add to int server, we call the spawn server, and we have turtle name plus x, y, and theta. Those are 4 arguments we need for the request. So we will create here spawn with spawn. So let's check here. Okay, the type is just spawn. There is no turtle before. It's just spawn. That is correct. We wait for the server. Okay, let's simply use waiting for server, and the request will be spawn.request. So we have first x to be x, request.y, request.theta, request.name, which will be turtle name. So we have matched all the field here. Now we call the client async method with the request. We get a future, and we add a down callback. Let's change this callback called spawn. So we have the future, and we actually want to get back the turtle name, x, y, and theta. So we have data for the response, which will be the name of the turtle. We will also get what name we tried to give, and then the coordinates. So instead of using that callback, I will use that one, and then simply do turtle name, which will be turtle name, x, y, and theta. Okay, I will remove that, and maybe we can just print get logger info. Let's say turtle plus response dot name. Let's check its name here. Plus is now alive. So we have a confirmation of when the turtle is alive. And actually, if response name is not empty, because if the response name is empty, it means that the turtle was not spawned. And how to know that? Well, you can simply try here from the terminal to spawn a turtle. For example, name it turtle1. If you name it turtle1, it will not work because the turtle1 already exists, and you will get a response with name. So that's how you know it is not successful. But note that even if the response here is not successful, the service call itself is successful. Okay, so we don't get the exception here. So great, we can call the spawn server, and now how we will do that? So I could directly call this function here from there. But what we want to do is to spawn a new turtle at a given rate. So I will create a timer, and in that timer we will spawn new turtle. So let's first create a callback for the timer. Let's say spawn new turtle, and in the constructor self spawn turtle timer self create timer with the time period. So we have to start with something. Let's say 2. So every 2 seconds we spawn a new turtle, and let's use spawn new turtle. Okay, and now we need to of course call this method here called spawn server with a name x, y, and theta, and we will make the coordinates random. Okay, and we choose a name that will change every time. So let's actually create a prefix and a counter. So here, self turtle name prefix. Let's say turtle by default, and a turtle counter, which is 0 at first. So the name will be the turtle name prefix plus the turtle counter, and we will increment the counter first. Turtle counter plus 1. So it means that the first turtle name will be turtle 1, then turtle 2, turtle 3, turtle 4, etc. Because we need to give a unique name every time. Now we need to choose X, and to choose X, I will actually use the random. So import random. I will use a random number, and I will do random uniform to have a number between 0.0 and let's say 11.0. So if you check the window here, 0 is here, and here it's something about 11, and also for the Y coordinates. So we will have a random coordinates in this screen. So let's do the same, random uniform 0.0 and 11.0. Okay, we can also add a orientation. Even if we don't use the orientation in the turtle controller, okay, we just want to catch the turtle, even if the orientation is not the same, but let's still create one uniform. So between 0 and 2 times pi, and of course we need to import the math library. Okay, and now let's simply call spawn server with the name x, y, and theta. Okay, great. So once we launch the node, we should see a new turtle every 2 seconds on the window here. So let's try that, and we first need to install the executable turtle spawner from the turtle sim catch them all turtle spawner main. So let's actually call will bytectg select with still the turtle, catch them all, and symlink install. Okay, let's put this here, and here let's do /rc, and now we will run Ros2 run turtle sim catch them all. We have 2 nodes, okay, turtle spawner and turtle controller. I will launch the turtle spawner to see if it works. Okay, we have an error. Yes, because the name of the turtle spawner here we need to do str because this is actually an integer. And now we can start it again. We have turtle spawning here, one spawning here. Here it's random, okay. So it is working. I can stop the turtle spawner now. As you can see, we have here an error for the first turtle. As I told you, the turtle should have a unique name. So we start with turtle 1, and actually the turtle 1 is the master turtle, what I call the master turtle right here. So you can create 2 times turtle 1. But in this application, it's really okay to just skip the first turtle, and then you have turtle 2, turtle 3, turtle 4, turtle 5, etc. Okay. So as you can see, we have 1 new turtle every 2 seconds on the screen. And now the challenge will be to ask this turtle to catch them all. This is step 3 of the solution for the turtle sim mini project. So for now, you already have 2 nodes in your turtle sim package. We will not add any other node, okay? We will improve them. The turtle controller, you have a controller, so you can actually have a target point and reach the target point from the master turtle. And in the turtle spawner, you simply spawn many turtles on the screen at a given rate. And now what we will do in this step is actually to create a publisher from this node to publish all the turtles that have been spawned and that are still alive. So the alive turtles will be published with Ros2, and turtle controller node will be able to subscribe to the topic, so it can receive all the coordinates for all turtles and then decide which target to reach. Because for now we have just created a arbitrary target, and we will actually target other turtles. So let's start by creating a publisher. And so to create a publisher, we need an interface. And what kind of interface will we use? Well, actually we will create one. Okay, so we will go inside our workspace. So here you have already my robot interfaces. So let's use that one. You could create yet another package that just for the turtle sim messages and services. You could also create the interfaces inside that package, but for this project I will use the interfaces package that we already have. So if you go to my robot interfaces, inside the MSG folder, we will create here not 1 but 2 files. Okay, I will create turtle dot, let's make it bigger here, .msg and turtle array.msg, okay, because we will send an array of turtles and we will actually create a new turtle type. So if you want to send an array of a new type, you can create the type and you can create the message for the array. So right here in, let's close that. In my robot interfaces, we can start with turtle.msg. And what do we need to send? Well, we simply send the basic info like name with string, then float 64 with the x coordinate, float 64 y coordinate, and float 64 theta coordinate. So if you find an already existing message type that you can use, well, use it. But otherwise, it's sometimes better just to create your own custom interface with also a name that is meaningful for your application. So we have a turtle with name and just the coordinates that we need. And then we can, in the turtle array, we can do turtle. So this is the type. We put an array and let's name the field turtles. So we have two new messages, turtle and turtle array. Actually, we will use turtle array to publish on the topic we will create. And let's go into symmetrix.txt. And here let's add msg turtle.msg and below that msg turtle array.msg. We can compile Ros2. Let's do calcon build packages. Select with my robot interfaces. Okay, and now let's see here. So of course I will need to source the bash rc because it's a new interface. And let's do Ros2 interface show so my robot interfaces msg, and we have turtle. Okay, and we have turtle array. Okay, so we have two new interfaces. Let's use them in here, turtle spawner. So from my robot interfaces.msg import turtle, we will import turtle, and from my robot interfaces.msg import turtle array, we need to import. Actually, we need to set a dependency for this here. Okay, because it's an other package than this one, and we need a dependency. So that's it here. So let's create our publisher. For example, here, self live turtles publisher. Self create publisher with message type turtle array with topic name alive turtles, and let's add a queue size. And I will also create a function so we can directly publish on this topic publish alive turtles. Okay, so I will create a message which will be turtle array, and actually message dot turtles will be, and we create here self alive turtles, which will be an array. Okay, so I will fill that array later. What we do now is to say that we publish it here, so self alive turtles, and in that array, of course, we will need to add some turtle object from there. Okay, because the turtle array is simply an array of this message, and that we can use as an object right here. So we do that, and then self alive turtles publisher publish the message. Okay, so now we need two things. The first is actually to store alive turtles when we can know there is a new turtle, and we need to publish it. So I will not create a timer here to publish alive turtles. We will do it directly from the callback of the service here. So when we spawn a new turtle, we get a response. We know here in this if we know that a turtle has been created with that name and that coordinate. So we can actually create a new turtle, put it in the alive turtles array, and publish the array. So let's create a new turtle, which will be a turtle object. That's why we imported this. New turtle will be, so the name will be turtle name as here. Actually, we can use response name, which should be the same, and then new turtle x new y, and let's do the theta new turtle. Okay, so now we append to the alive turtles array, append new turtle, and what we do directly after that is self publish alive turtles. So whenever we create a turtle and that is successfully down, we add a new turtle object here to this array, and then we call this function to publish the array. Let's try that. So we used symlink installed before, so I can launch it here, but I will first source the bash rc because we are using new messages. Okay, Ros2 run my turtle sim catch them all with spawner, so turtle spawner. And if we want to do that, also first we need to run turtle sim node. Okay, we have our turtle here. So I start the spawner. Let's see what happens. Okay, so the turtle one already exists, we know that, and new turtles are being spawned. So Ros2 topic list. Okay, as you can see, we have new topics for every new turtle, and we have the topic alive turtle. So I will source bash rc because this is a new type. Ros2 topic echo alive turtles, and let's see what we have here. Okay, I will press Ctrl+C and just see one message. So as you can see, that is an array. We have turtles, and then for each turtle, you have the name and the coordinates. Okay, for every turtle. So as you can see, every time the array will grow by one turtle. So let's kill the spawner. Okay, so that's a lot of turtles to catch, right? And now from the turtle controller, we actually need to listen to that topic so we can get all the turtle information. So let's do that. Turtle controller, we will import. Let's import both from my robot interfaces.msg import turtle, and let's also import from my interfaces message turtle array. So we create a subscriber, and we will also create a callback. Call def, so callback alive turtles. Okay, and let's create a subscriber right here. Self alive turtles subscriber with self create subscription. Message type is turtle array. The name of the topic is alive turtles. Let's make sure it is the same as here. And then we have callback, self callback, alive turtles, and AQ size. Let's format this. Okay, so the live turtle subscriber is now up with a callback, and we have imported the type here. And what we will do now, we will remove that. And instead, we will create a turtle to catch object for now, which is known, okay? And we will simply fill it from this callback. So first we check that the length of message turtles is greater than 0. So if there is no turtle, we don't do anything here. Of course, if we have at least one turtle, what we will do is say that self turtle to catch will be the first turtle. 0. Okay, and we will improve that code later on in the following part of this solution. So just for now, we take the very first turtle. So it means the turtle that was spawned first. So when we receive the first callback here, we have a new turtle here. So in the control loop, we don't have target X and target Y anymore. What we will check here, first we check if we have a pose, but we'll check also, so if pose is known or we don't have any turtle to catch. So basically it means that we don't go inside the control loop if we don't have the current situation and if we don't have the target. Okay, that makes sense. And here, instead of using this target X, we will use turtle to catch X, and here, turtle to catch Y. So target minus current is the distance here. Let's check that everything else is correct. So as you can see, we don't change anything in the control loop here, just the data we get for the target, and the rest is the same. So let's launch that. Okay, we have our, okay, let's start everything again. The turtle sim node here, the turtle spawner, and here we will Ros2 run turtle sim catch them all with the Ros2 run turtle sim catch them all with the This is step 3 of the solution for the turtle sim mini project. So okay, we have our, okay, let's start everything again. The turtle sim node here, the turtle spawner, and here we will Ros2 run turtle sim catch them all with the turtle sim controller. Okay, I will run the controller first, and it should not do anything because we don't have a target yet. If I start this, it will try to spawn. Okay, the first one doesn't work, and then it will spawn. Okay, it will spawn the first turtle, and it will publish the list of alive turtles. This node, the controller, will receive that list, and will start to go to the first turtle, and then this will continue to publish to spawn other turtles. But here, as you can see, the turtle just stays around the first one. So what we need to do now is to say, okay, this turtle has caught this one. Now we need to remove it and go to the next one. this is the step 4 of the solution of the mini project with turtle sim. And right now you should have, so you have a turtle spawner that is spawning turtles and is publishing the alive turtles on this topic. The turtle controller will receive the list of turtles by subscribing to the topic, and then we'll decide to chase the first turtle, so to catch the first turtle of the array, and we have a control loop to do that. So to finish the application, what we need to do now is to say that when we caught the turtle, so when the master turtle has caught a turtle, it should remove that. So the turtle controller should tell the turtle spawner that it has caught a turtle. And then we will use the, okay, if I start turtle sim node, if I do Ros2 service list, we have used spawn to spawn a turtle, and you have kill. Kill will simply remove a turtle from the window. So if you ask to kill that one, which is turtle one, then poof, turtle one will disappear. So that's what we will do for every turtle that is caught by the master turtle. And here what we will first do is that the turtle controller will call a service in the turtle spawner. We will call the service catch turtle. And then the turtle spawner will call the service kill from the turtle sim node. So why are we doing that? We could directly, from the turtle controller, we could directly call the kill service to kill the turtle, but then we also need to notify the turtle spawner, because the turtle spawner keeps the alive turtle, so it needs to know which turtle to remove from that array, because then it will send the array to the turtle controller, and if the turtle that was killed is still in the array, then the controller will continue to follow that turtle, even if it is not here anymore. So let's start. Let's start with the service server catch turtle. So we will create a new service with so my robot interfaces in the SRV touch catch turtle.srv. Okay, interfaces, it's here, and simply let's give the name of the turtle and bool success. So this service is quite simple, right? The turtle controller just said, hey, I just caught this turtle with that name, and that's it. Do whatever you want. So we can add it here, srv catch turtle.srv. Now we can add it here from my robot interfaces srv import catch. Okay, and actually this is specific to VS Code here, but the path for the Python for the auto completion is in the install folder of the Ros2 workspace, which means I need to build first the package, my robot interfaces. Okay, and now the interface package has been built. We can find it here, catch turtle. So let's create our service server here with also a callback. So we'll add callback here, def callback catch turtle with request and response. Let's put it here, self catch turtle service with self create service catch turtle as a type. Let's use catch turtle. So again, we use a verb and the callback, self callback catch turtle. Okay, and what we need to do in that callback now is to call the kill service here. Okay, so you can totally do that. You are in a callback for a service server and you call another service. So let's see what we need to do here. Ros2 service type kill, and this is from the turtle sim package again. So let's do Ros2 interface show kill, and okay, we can see that we just need to give a name here as a string, and we don't have any response field, so we still receive a response, but the response will be empty. So let's call this from the turtle spawner node. What I will do is simply use that as template and to copy and paste that. So I will directly rename. So okay, I will use call kill server with the turtle name only. We will use kill here, and actually it's better if we import it before. Let's import it here from turtle sim.srv import kill right here. So kill client wait for service, and then the request will be kill.request. We simply have name, which is turtle name right here. We call the server with call async. We get a future, we add a done callback, and let's use callback call kill. We just keep the turtle name and callback. Let's rename it here. Okay, we don't need that. And actually, I will remove that also because it's from the spawn functionality. We will not check what's inside the response because there is no response. But what I will still do is to actually try to call future results. Okay, why do I do that? Because when you call that, you may have an exception. The exception when the service call failed. Okay, so if the service call failed, at least we will have the exception and we will have the log for the exception. Okay, if the service call is successful, then this will simply return an empty response. And then we know that when we reach that line, the service call was successful. And now, and that is the important thing, what will we do in that callback? Because when you ask to kill a turtle, the turtle will disappear. The turtle will disappear from the screen. So we will need to make it disappear also from the alive turtles array. So when we publish the array the next time, the turtle will not be here anymore, and the turtle controller can then switch to a new target. So we have the turtle name here, that's why I passed the turtle name here. So now we can find, actually we can find from the alive turtle array, we can find the turtle that has the same turtle name and remove it. So I will use for I turtle enumerate self alive turtles. So I'm just going to do a for loop inside the of turtles, but I also need the index, so I use enumerate. And let's check that if turtle dot name is equal to the turtle name we have here. So the name from the turtle in the alive turtles, if it's the same as the one we just killed, we will do del self alive turtles with index I. So we just remove it from the array. And then let's use a break, because once we have done that, we don't need to go through all the other turtles in the array. And one thing I will add here is simply to call publish alive turtles, because we've just modified the alive turtles array. So I will directly call this so we can publish the new array. Okay. So when we publish this array is after that we have spawned a turtle and after that we have removed a turtle. So the callback is good. Okay, now let's come back to the callback for the catch turtle service. And here we will do self call kill server with request dot let's see here, request dot name. Okay, so this expects a boolean success for the response. So let's say response dot success equals true. Okay, I will just put true like that and just return, don't forget that with Python, return the response. So what will happen when we call from the turtle controller, the catch turtle, then we get to that callback, and here we call yet another server with a new client with kill. And when the turtle sim node has replied, we remove the turtle and we publish the new array. So the turtle controller will receive here callback alive turtles. It will receive a new array and it will be able to switch because the first turtle in the array will not be the same. Okay, and finally we need to call the catch turtle service from the controller. So let's add it here, and I will use the same template like that, and I will put that here, for example. Okay, it will be called catch turtle server with the turtle name catch turtle. The name is catch turtle. Okay, the request catch turtle dot request. Then the callback let's name it callback call catch turtle. Okay, let's keep that parameter here and let's modify the callback here. And of course we remove that. Here we will check the response because it contains a boolean flag, and let's say that if response success. So if not response success, we will print an error, self get logger error turtle, and let's put turtle name could not be caught, for example. So if we succeed, we don't print anything. If it fails, we will print a log message in that case. And finally, the last thing we need to do is to actually call this function. And where we will call this function? Well, simply from the control loop when we have reached the target. So here, target reached means that we have reached the turtle. So we can do self call catch turtle server with the turtle name, and the turtle name is actually self the turtle to catch dot name. And actually, let's check here. Yes, request. I have created the request, but I have not filled the request. So if I don't do that, I will get an error. Let's put turtle name inside the request. And seems that we need to import partial. So yes, from func tools, import partial. Okay, let's run this to see if it works. So Ros2 run. So we'll always launch the turtle sim node first because it is required for both the other nodes. Let's that Ros2 run turtle sim catch them all with the controller, turtle sim controller, and Ros2 run turtle sim catch them all with the turtle spawner. So let's start, for example, this controller and now this spawner and see what it does. So one turtle is okay. We have an error here. So it's working, but we then have an error. Tried to kill turtle switch, which does not exist. Yes, because the problem comes from if we go to the turtle controller here. When the target is reached, we ask the turtle server to actually catch the turtle and then to kill the turtle. But until we receive a new array with new turtles, this turtle is still the turtle to catch. So at 100 Hz, it will still call this service. So what we need to do once we have found it is to do self turtle catch. Now, okay, so when we have reached the target, it's useless to continue running the control loop because we stop, and it's useless to send hundreds and hundreds of calls to the server. So now let's run this again. Okay, because we still have a controller running. So we kill everything. And okay, run controller. Run turtle spawner. So we have first turtle. Okay, and it's working. So as you can see, when you start a Ros2 program, it's often not working the first time. And here, great. As you can see, when the turtle reaches another turtle, it will call the catch turtle for the spawner node, and then the spawner node we call the kill node here, and the kill node will then return okay, and then we can remove the turtle from the array, and then it comes back to the controller, which now has a new target. Is step 5 of the solution for the turtle sim mini project. So now everything is working. We have a turtle controller, a turtle spawner, and the communication between both is correctly working, so the turtle controller can catch a turtle and then switch to the next one. But we will add a little improvement here. Instead of, okay, when we receive the alive turtles from the topic, alive turtles, we always try to catch the first turtle in the array. Now what we can do as an improvement is to catch the closest turtle, not necessarily the first turtle, okay? And to see that, we can first add, we can increase here. So we create a new turtle every 2 seconds. Let's now create, instead of 2 seconds, let's put 0.5 to see what I'm talking about. I start the turtle sim node, I start the spawner, it will spawn many turtles, and I start the controller. Okay, and you can see the turtle is catching other turtles in the order with which they appeared, okay? And now, in order to make it more efficient, instead we could ask the turtle to catch the closest turtle, not necessarily the next one in the array. Okay, so let's do that. So I will simply work in this callback, and well, that is just a function to write differently. So first of all, maybe we still want to keep the option to get the first turtle. So I will add a new flag here, self catch closest turtle first, which will be true in that case. And here I will do yes. So here first we check if we have any turtle in the array, and then if self turtle catch closest turtle first, then it's what we will do right now. Else we will get the first turtle in the array. So here we will simply compute the distance between the current pose of the turtle and all the turtles in the array and find which is the closest one. Okay, so I will create 2 variables first: closest turtle, initialized to known, and closest turtle distance, also known, just to help with the program. And then for turtle in the turtles, from the message we will do, so the distance x will be turtle.x minus the pose x. Same for distance y minus self pose y, and then the distance will be, let's check that we have the math. Yes, square root, as we did before, as the addition of the 2 square number, this y times this y. Okay, so we have the distance between the master turtle and the turtle in the array. If closest turtle is known, so basically this is for the first case when we don't have the closest turtle yet, this turtle will be the closest turtle. Or if the distance is less than the closest turtle distance, then the closest turtle will become this turtle, and of course we have closest turtle distance, which is the distance. Okay, so the first time for the first turtle, the closest turtle will be the turtle, and the closest turtle distance will be the distance with that turtle, and then we will check with this that the distance of the new turtle, is it lower or greater? If it's lower, then we update the new turtle, And when we finish with this for loop, simply we do self turtle to catch will be equal to the closest turtle. Okay, and now let's restart everything. Start turtle sim node, start the controller and the spawner. Okay, so it is catching turtles, and as you can see, it is not following the order of operation of the turtles. It is always going to the closest turtle. And here, did you just see that? It was going to that turtle, and a new turtle spawned, and it just changed the direction. Okay, so that is the way that is more efficient to catch turtles. Great. And well, of course, here the frequency for spawning turtles is a little bit too high. Let's try turtle spawner with 1 Hz. And actually, we will make parameters of that in the next step. So if I start everything again, but with 1 Hz, now we should have something that is okay. Let's put this. Okay, as you can see, it can follow the turtle spawner. It's not too fast. Okay, up we catch this one, this one. This is finally the last step of the solution of the mini turtle sim project, and in this step we will not actually add new functionalities to the code. We will simply make it more scalable by using parameters and starting the whole application from a launch file, okay? Because for now we have used 3 terminals to launch 3 nodes, and as you can see, when I changed some value, for example the spawn rate, or if I need to change some value, I directly change them from the code. So first we will add parameters, so we can change them directly from the terminal, and then we will put everything into a launch file. So let's start with the turtle controller node, and here I will only add 1 parameter. It's actually the flag here, catch closest turtle first. Because maybe you want to catch the closest turtle first, maybe you don't want to, and you can specify that with a parameter. So I will add it here, self declare parameter, so always declare first your parameter, catch closest turtle first. And let's put a default value, true. Okay, and now what we do, I will put that here, is instead of true here, we will do self get parameter with that name. And don't forget dot value. Okay, you could add other parameters if you want to, for example, the control loop frequency here, I will keep it at 100 Hz. For now, I will just use a parameter for that. And let's add other parameters in turtle spawner node. So here, what we really need is the spawn frequency. So I will do self declare parameter spawn frequency. Let's put 1 Hz by default. Okay, and I will also add another parameter, declare parameter, which will be the turtle name prefix, because here it is turtle. Maybe you want to name your turtles with another name. So I will keep the default to turtle. And of course, what we can do is self get parameter with that dot value. And we can add the spawn frequency, which will be self get parameter with spawn frequency dot value. So here what we can do is, okay, that is the period, it's not the frequency, so we can do 1 divided by the frequency, self spawn frequency. Okay, and that's it for parameters. So you can see it's quite easy here. You just declare parameter with name, default value, and you get the parameter with get parameter and dot value, and finally you just use them in your code. So for those 3 parameters, the spawn frequency, turtle name prefix, and the catch closest turtle first, you can use them directly from terminal with Ros2 and -p. You already know how to do that. And now we create a launch file. So again, we will create the launch file in my robot bringup to make it simple, just as we created the interfaces in my robot interfaces. Let's create a new file here. So let's go inside my robot bringup, launch, and touch turtle sim, catch them all. Okay, that will be the name of the application. .launch.i chmod plus x turtle sim catch them all. Okay, and we can now edit the file. Okay, so let's import the launch import launch description. Let's import nodes also from launch Ros actions. Import node. We create the generate launch description function. We create the launch description object, and at the end we will return the launch description. And now let's add the 3 nodes we need. So the first node is turtle sim. Turtle sim node is from package turtle sim, and the executable is turtle sim node. Okay, that is what we have here, turtle sim node. So we will add it here, ld.add action turtle sim. Let's actually call it turtle sim node. Okay, and because we use the turtle sim package, I will add dependency here, exec depend. So in the my robot bring up, exec depend turtle sim. Okay, so turtle sim node will be started. We also need the spawner node, turtle spawner node. So from package, turtle sim catch them all. The executable is turtle spawner, and we will have some parameters which are spawn frequency. Let's put 0.5 here, and the other parameter is turtle name prefix. Let's set it at my turtle to make it different from the default value. Okay, and we can add the add action turtle spawner node. So we have turtle sim node, turtle spawner, and now let's start the turtle controller node, which is from package turtle sim catch them all. Okay, that package actually, as we use it, we need to also add a dependency here, exec depend catch them all. Okay, so we have another dependency in the package.xml of my robot bring up package, and the executable name will be turtle. Okay, if you have doubt, just check out what you've written here, and it is turtle sim controller. Okay, for a reason, I don't know which reason, I chose to use turtle sim controller for the executable and turtle controller for the node and the file name. So, but that is the executable we want. Let's use that here, and I will add parameters. Actually, we have one parameter which is catch closest turtle. First, I will set it to true. So the default value is true, but I still set it to true. Okay, and okay, let's add it here. Add action turtle controller node, and that should be it. So as you can see here, I don't rename or remap any topic. You can play with that if you want. Okay, to practice more, I just start the node with package executables and parameters if needed. Okay, we can start this launch file. So first, let's compile again. Cocon build with packages select, and let's use my robots bring up. Okay, we have an error. Why is that? Because in the package.xml, yes, package.xml, I have used exec depend to start the tag and depend to close it, so it's not correct. Let's compile again, and it's working. So now let's source this terminal /rc, and okay, don't need that anymore. And let's do Ros2 launch my robot bring up with turtle sim catch them all launch by, and let's see what we get. Everything is started, and it seems that it's working. So as you can see, from one terminal we start the window, the turtle sim node, the turtle spawner, and the turtle controller node. And if you want, you can directly go back to your launch file and change parameters. So yeah, we publish at 0.5 Hz. Let's publish faster at 1.5 Hz. Let's give that actually. Yeah, I will show you what is the result with that. So we start it again. Now it's publishing much faster. Okay, the spawning is much faster. And if we Ros2 topic list, you can see that the turtles are named my turtle plus a number. Great, so the turtle sim project is now finished. Congratulations if you made it until that point. With Ros2 bags. So let's first start with the problem. Let's say you want to test your robot in real life, and for example with specific conditions, like you want to test a mobile robot outside while it is raining. So you find the perfect spot, the perfect day where it is raining, and you start your robot. But now you will not have that spot and that condition every day, every week when you need to work on the robot. So what you can do with Ros2 bags is actually to save the data you got when you actually started your robot, and you can play it later exactly as it was recorded, so you can analyze it and continue to work on your robot. So to start a bag, I will first need a topic. So I will launch Ros2 run my Python package. I will launch the number publisher node, which we publish Ros2 topic list, which we publish on the number topic. Here we are in our home directory, and we create folder bags, so we can store the bags here. And let's do Ros2 bag. Okay, press tab twice. You can see we have 3 actions that are possible. Record, factory record topics. Then we will be able to play them, and we also can get information about a Ros2 bag. So let's use record. You then put the name of the topic, number. If I just do that, it will start listening to the number topic. So if we create a subscriber to the number topic, okay, if I kill it, it will stop the subscriber. And as you can see, the name of the bag is Ros2 plus the timestamp. So what we can do here is actually to use O to specify -O for output, to specify a file name, which may be more useful. I will just use test here, okay? So here again, it will store messages inside a database. So it will be a SQLite database, which is a database inside a file, and it is listening to the number topic. So I will wait a little bit so we have more data. And as you can see, we still have the number publisher, which is publishing here. So now it should be okay. I press Ctrl+C to stop. I can also stop the publisher, okay. And with Ros2 bag info on the name of the folder, you have information about that bag. You can see the bag size here, the duration, okay, which is about 30 seconds, the start and date, and the number of messages inside the bag. So we have 31 messages, and you have all the information about every topic that were recorded. So what we can do now is to replay that bag. So we don't have anything working right now, okay. We don't have the number publisher. Ros2 bag play test. So it will open the database and start playing it. If I do Ros2 topic list, we can see we have the number topic, Ros2 topic echo number. We are getting the number not from the publisher here, but from the bag, which is publishing now the message that it was recording before. If I start Ros2 run my Python package, let's start the number counter node, okay, and let's see Ros2 topic echo number count. Okay, as you can see here, the bag now is not playing anymore. Why that? Because we have recorded for 30 seconds. So of course it will play back the data for 30 seconds. If you record for 1 hour, you will be able to play it for 1 hour. So we will start again. Okay, and as you can see now we have the counter because we just started a publisher on the number topic. And if you wait 30 seconds, it will stop. And of course the number counter will not receive any more message. If I kill it, we can also stop it. Great, and you can also record multiple topics at the same time. Let's say now I am starting the launch file, my robot bring up. I am starting the number app launch, which will start the number. Okay, let's see what we got here. Ros2 topic list. We have my number and my number count. So we have 2 topics, and those are also renamed. So I will do Ros2 bag record with my number and my number count -O. Let's say test 2. You can't record 2 bags with the same name. Okay. Let's press enter, and it is now subscribing to my number and my number count. So 2 topics will be recorded. I wait just a few seconds, and now I can kill. Okay, let's do Ros2 bag info test 2. As you can see, we have here so 138 messages, okay, and we have 2 topics, my number count with this type, 63 messages, and my number 75 messages. Okay, I kill that, and now you can do Ros2 bag play with test 2, and it will replay the data exactly like it was published. So Ros2 topic equal my number count, and as you can see, we have the counter just as it was recorded. So it's not starting at 0, because when we recorded it, it was starting already at a higher value. So we get the exact values here. And now the play has finished, so we don't get any new message. And finally, if you want to record all topics, you can not specify any topic inside, you put -A for all. Let's say test 3, and that, as you can see, will record all topics. So maybe it's better if we start something. Okay, test 4, and it is subscribing to Ros2, my number count, parent build event, and my number. Great, so you have seen how to use bags in your application. That will save you a lot of development time.